Okay, hi everyone. I hope you can see the first slide. My name is Ali and I'm an assistant professor at Louisiana State University. And I'm going to present part of my PhD work, which I did at the University of Southern California with my PhD advisor, Dr. Bero Koshnevis. And the topic of my presentation is real-time extrusion quality monitoring techniques for construction 3D printing. I think by now we all know about different applications which can be considered for this amazing technology of construction 3D printing, low-income housing, emergency construction of shelters and houses after a natural disaster happens. And we have seen demonstration projects for 3D printing of bridges or towers. And of course, the space applications that actually the previous presentation was all about. And I just want to highlight the value of having an automated construction technology in these unusual times. You might have heard about the emergency hospital, which was built in China in just 10 days for coronavirus patients. So I think this would be a perfect scenario for using an automated construction technology such as construction 3D printing. So there's definitely a significant need for a fast, reliable, and efficient technology like construction 3D printing, but there are a lot of technical and regulatory challenges that have to be solved first. Actually, later today, Dr. Mahmoud Ekenal is going to talk about AC 519 and the major advancement that we have with respect to building code compliance of 3D printed houses. But in terms of the process itself, I think robustness and quality control is a key element, which is going to determine the success of this technology. I think this short video is going to help making my point. You can see a freshly printed wall which collapses, and you can see actually me sitting right there, a few years younger, and learning a lesson from this failure. And just imagine in the middle of like printing a house, like half of the height of the walls are printed, and then suddenly something like that happens. That would be a disaster in terms of waste of material and time and resources. So that's why I think quality control is very important, and it needs to be addressed like any other fabrication process, but in the construction, the product is a house, which is very big and also very important because people are going to live in these houses. So the quality of the product is very important. In conventional construction, the on-site quality control for fresh concrete is usually simple and basic, which is okay because the requirements don't need much more. Like we are casting a large amount of fresh concrete in a short time, and as long as the structural and durability requirements are met with the hardened concrete later, we are fine. We are not concerned with fresh concrete that much. But it's a different story when we are dealing with construction 3D printing. There are more challenging requirements in terms of fresh concrete, and that's why I think we need an inline, reliable, real-time quality monitoring system for construction 3D printing. And based on that, as I said, part of my PhD work was focused on developing real-time extrusion quality monitoring techniques in order to be able to detect variations in the printing material. Of course, there are other aspects like failure in the hardware components, the software and everything, but my work was focused on material variations. And the idea was to implement these ideas and evaluate each of them under simplified laboratory conditions. And you can see the 4 techniques which I designed and studied in my work. But today, because of the limited time that we have, I'm gonna go through 2 of them, the power consumption measurements for the agitator motor, and also using computer vision for real-time extrusion quality monitoring. In terms of material variations, I think one of the most common issues is the variations that we have in the free water of the printing material. In conventional construction, we also have this problem because the accurate measurement of the moisture content in the aggregates, especially sand, is not really easy. So based on that, I selected that as the source of variation, and then I designed 6 levels of variations that you can see in the table. I have a reference mixture, I called it QC-ref, and that was basically from a previous study that I did in 2017 with respect to performance-based testing of fresh concrete in construction 3D printing. And then I intentionally changed the amount of free water in this mixture by plus minus 5, 10, and 15 liter of water per cubic meter of concrete. And I should say plus minus 10 is usually the number that is used for variations that we have in conventional construction. For example, for self-compacting concrete, we usually use plus minus 10 as the amount of variation that we should be able to deal with. So I added 5 and 15 so that I can have a good idea of the performance of each technique against different levels of variation. As I said, the first technique is based on the continuous power consumption measurements of the agitator motor. And this idea can be described as embedding an inline viscometer or torque meter in the wet material circuit flow. And at least when I started, there was no other data or implementation of this technique, but in other areas of concrete technology, something similar was done. Like in 2007, in a study, a researcher basically measured the power consumption rate of the concrete mixer motor and use that to describe various stages of concrete mixing and develop a graph like what you can see here to have the power consumption evolution basically at different stages. So here to implement this idea for construction 3D printing, I designed agitator blades and 3D printed them using ABS plastic. And as you can see, the design was basically inspired by those commercial continuous mixers, the blades that they have. But the functionality is really more like the paddles of viscometer that you might have seen in the lab. And I installed 5 of these blades on a shaft connected to a DC motor. And for each test, I used the average of the readings during a 10-second period, and I repeated the experiment for each of those variation levels 4 times, and I used the average as the result of that test for a specific variation level. Here you can see the results. The standard deviation was in the range of 1.6 to 4.4 watts, and as you can see, as a general trend, as the amount of water in the mixture was increased, the power consumption of the motor was going down, which makes sense because the viscosity of the printing material goes down by increasing the water content. And other than that general trend, you can see that in the range of -5 to +10 liter per cubic meter, we cannot really see any change. We cannot see any statistically meaningful change in the extruder power consumption. So basically this technique is not able to differentiate between these 4 levels of water content in the printing material. And also another observation that I had was that in the lower level of water content, like -10 and -15, we had a larger change, bigger change in the power consumption. So basically there was more response in the power consumption when we had more viscous printing material compared to like +10 and +15 liter per cubic meter. So the system was more responsive when we have lower amount of water and more viscous mixtures in the hopper agitator system. And based on that, the variation levels that basically were detected by this technique were -10, -15, and +15 liter per cubic meter. The second technique was using computer vision, which you might be familiar. It is used as a tool for example, automated construction monitoring. for tracking, construction machinery and materials on the construction sites. And here, the idea was based on the observation that changes in the properties of the printing material results in over extrusion or under extrusion conditions. So for example, at a fixed printing speed, reducing the viscosity of the material can result in a wider layer and basically over extrusion. And based on that, we wanted to have a vision system which is able to measure the width of the layer in real time to detect material variations. And I should say that this whole idea of using computer vision during the construction 3D printing process was patented by Dr. Koshnevis, which you can see on the left side. And then the picture on the right side shows the configuration that we designed for these experiments, having a camera at a fixed distance from the extruded layer, and then using the extrusion videos and analyzing that using a single board computer called Raspberry Pi and OpenCV library, which is a set of real-time computer vision functions developed by Intel. Here is a flowchart for the algorithm that I developed for this real-time analysis of extrusion videos. I'm not going to go into all the details because we don't have enough time, but just a few points I'm going to mention. For example, the frequency of grabbing frames, it can be automatically calculated based on the nozzle traveling speed and the camera speed in terms of frame per second. And also after all the processing, pre-processing of every video frame, all the contours are extracted in an image, and sometimes we have some invalid contours. And to eliminate those, I basically applied some size and shape discrimination techniques using parameters such as contour extent and contour area, as you can see here. So a video frame like this would be automatically disregarded by the algorithm. And in terms of calibration, I want to first have a reference layer with accurate dimensions. So instead of printing the layer, I printed a mold, and I basically used a self-leveling concrete to cast a nice layer with exact dimensions of 1.5 inch width and 1 inch height, and then use my vision system to measure the width of that layer. And it was consistently measured at 63 pixels, which gave me a pixel per inch ratio of 42. And you can see the picture on the right side. And then to verify that, I basically created and fabricated another layer with a different width of 2 inch and used the system, which basically this second measurement exactly verified the pixel per inch ratio that I selected and showed the high precision of my system before the main experiment. And here is a demonstration of system for a case which was actually over extrusion. So here the target width of layer was 1.5 inch, but because of the over extrusion, the layer width was more than that. And as you can see, the system can measure that in real time and report the width of the layer. And these are the actual variations for the main experiments. The reference QCref, as I said, it was designed for 1.5 inch width. So it was around 38, 39 millimeter, which was based on the design. And then different various amount of water, which affects the width of the layer. If you see the variations and the average width for 4 layers for each experiment, you can see that basically at each variation level, even the lowest ones, we are able to see a significant change in the width of layer, and there is no overlap. So basically we can see a meaningful change in the layer width as a result of changing the water content. And also in 2 cases, because of the low amount of water, we couldn't extrude a continuous layer. So I could see the tearing or even zero deposition for those mixtures. And in those cases, the system was able to detect that as under extrusion. It couldn't differentiate between tearing or zero deposition, but it would report both of them as under extrusion. So it was detected for both cases. And we can say that for all of the variation levels, all of the 6 variation levels that I designed, the system, the technique based on computer vision was able to detect those variation levels. And to quantify the responsiveness of each technique against material variations, I used a sensitivity index, which is usually used in other areas to provide the separation between the means of signal and noise distributions compared to the standard deviations of signal and noise distributions. And here you see the values of sensitivity index for each variation level for each technique. And as you can see, even at the lowest variation level for computer vision, we are having the sensitivity index of 2.8, which means that the changes in the width of the layer is almost 3 times more than the variations in the measurement, which translates into a very reliable detection even at that low variation level. And of course, as the variation level goes higher from 5 to 15, the value of the sensitivity index goes higher, which means even better and easier detection of the variation level. And power consumption technique, as you can see, for 3 of the variation levels, plus minus 5 and plus 10 liter per cubic meter, it was not able to detect the variation level, the variation in the printing material, but for the higher levels, it could easily detect it with very high sensitivity indexes. So in general, I could say that the technique based on computer vision had a better performance, a high accuracy, and a very high sensitivity to and responsiveness to variations in the material viscosity. And one reason that comes to my mind is that that technique is based on direct measurement of the properties of the system output rather than relying on a correlation between the viscosity of the material, for example, and printability or other properties. And with that, I want to thank you all, and I'll be happy to answer any question that you might have.
Okay, thank you very much.